Hello, this is Jack Jackson. We're going to look today at antiderivatives and definite integrals. And we're going to find how we can find formulas for antiderivatives and use those to find exact values for definite integrals using the basic rules that we talked about in the last video. So we're going to do several examples. In these examples, we're going to do several things. We're going to, first of all, find the family of antiderivatives for a function. Then we're going to check that both by hand and with a graphing calculator. We're also going to find an exact value of a definite integral, and we'll check that with the calculator. And we'll also find a specific antiderivative given an initial condition. And we're going to start with the easiest ones I can think of, and then we're going to just kind of build up from there. So this first video here on this sort of idea and technique will involve just the most basic examples. So we have the first question here is going to involve the power rule. So we're going to take the following family of antiderivatives, the antiderivative of x to the ninth dx, and let's find that. Well, it's a pretty simple rule. You just take the power and add 1 to it, so it becomes from 9, it goes up to 10. And you multiply by the reciprocal of that power, which is 1/10, and then we add a constant. And there it is. That's all there is to it. Pretty simple. Now we want to check this with and without a calculator. And so, without a calculator, what we're doing is taking the derivative of our answer and seeing if that's what we started with. So we want to take the derivative of this right side, and we should end up with the x to the ninth that we started with. That's what it means for it to be an antiderivative. And of course, when we do this, we use our derivative rules. First of all, the derivative of the sum is the sum of the derivatives, and the derivative of the constant is 0. So that plus c being there, we notice that the derivative of that part will always be 0. So when we take the derivative of this first part, we have 10 times 1/10 is 1, and power goes down 1 to 9, and so we get x to the ninth. Pretty basic. Now, we can always check any derivative problem using our calculator by putting what we want to take the derivative of as y1. Let the calculator put in, or we put in the calculator, the numerical derivative of y1 with respect to x, at x. That is this in the newer operating system on a TI-84. In the middle picture here, in the left picture, that's what it looks like on the older 84s and the 83s. And then the answer down here in y3 is the answer to our derivative problem. Well, before when we did this, we were doing derivatives, we put the problem in y1 and our answer in y3. But now we're doing an antiderivative, that's backwards. Our answer to our antiderivative problem is going to go up here in y1, and the original is going to go down in y3, the thing that we're integrating, the integram. Okay, now let's do that. This case, 1/10 x to the 10th was our answer, our antiderivative. So if we take the derivative of that with respect to y, the derivative of that y1 with respect to x dx, this is of course a symmetric difference quotient, a approximation of the derivative. And then the real derivative should be the thing we started with, x to the ninth. We check to make sure the tables for y2 and y3 match, which of course they do. Now, if we're looking for a specific antiderivative, remember that if g of x is an antiderivative of f of x, which is x to the ninth, then what we're talking about here is g of x, we know, is 1/10 x to the 10th plus some constant. Okay, make that disappear. There we go. Okay, so it's g of x is 1/10 x to the 10th plus some constant. Well, if we don't know which constant that is. It could be any constant, and it would still be an antiderivative. But if we have this point right here, g of 1 equals 7, that tells us an x and a y coordinate on the function g, and so we can plug that in. We plug in the 1 for the x and the 7 for the g of x, or for y, and solve this for c. Now we got an equation that only has c. Of course, 1 to the 10th is 1, so 7 equals 1/10 plus c. Subtract 1/10 for both sides, get a common denominator. 7 is 70 tenths. 70 tenths minus 1/10 is 69 tenths. Plug that back in place of c because we found that c is 69 tenths. So g of x is 1/10 x to the 10th plus 69/10. Usually we prefer fractions like this if we're trying for exact values, because oftentimes fractions, sometimes they'll terminate, but oftentimes they will, most of the time they will repeat, and unless we can see exactly what that repeating pattern is, we only get decimal approximations when we try to use decimal form. But in this case it terminates very quickly, so we could also write that in decimal form as g of x equals 0.1 x to the 10th plus 6.9. Alright, so far we've just done antiderivatives. What does this have to do with actual integration, that is definite integrals? Well, we use the Fundamental Theorem of Calculus for that. So if we're given the problem of trying to integrate x to the 9th dx from 1 to 2, a definite integral, we find an antiderivative, which is 1/10 x to the 10th, and evaluate from 1 to 2. Notice we do not need to put the c here, because it would just, any c that we would put in would just cancel out. This notation here, 1/10 x to the 10th, and it's such that, or x goes from 1 to 2, what that means is we evaluate it at the top number, which is our top limit up here, by plugging 2 in place of x, and then we plug 1 in place of x in the bottom one here. So this is 1/10 times 2 to the 10th minus 1/10 times 1 to the 10th. Okay, so 1 to the 10th is 1 times 1/10 is 1/10. 2 to the 10th is 1024, and that's times 1/10 is 1024 tenths minus 1/10 is 1023 tenths, or 102.3. That's an exact value for that definite integral. We can check that using our calculator by just doing the numerical integral on our calculator. If you have the older operating system, like if you have a TI-83, it would look like this, and you push math 9 to get that, and that's function integrate or numerical integration. Put the formula in here that you're integrating, x to the 9th. This x is like the dx. Both cases it's notational, telling you that x is the variable. And then this is the lower and upper limit, and we get 102.3. In this case it worked out exactly correct, which is the exact answer. Or if you have the newer operating system on a TI-84, it would look like you would write it. It looks just exactly like the given problem, and that's what you get for the answer. And so that did check out. Okay, now let's look at another example here. This is another power rule example, but this is sort of the exceptional case where the power is -1. If we try to use the normal rule for powers, just notice it would not work. We add 1 to the power, we get a power 0, and when you try to multiply by the reciprocal of 0, it doesn't work. But we do know how to do this one. This is our special rule for these. Remember, x to the -1 is another way to write it as 1 over x. So whether you think of it as the antiderivative of x to the -1 dx or the antiderivative of 1 over x dx, either way you get the natural logarithm of the absolute value of x, of course always plus a constant. Why do we know that? Well, because, and how do we check it? We take the derivative of our answer, again always the plus c, derivative is 0, and the derivative of natural log of absolute value of x is 1 over x, which is x to the -1. So that does check out, and once again we can also use the calculator to check it by putting our answer in, ln absolute value of x. Again, you can put a plus c if the plus a particular number there if you want, or not, and then the derivative of y1 is y2, and then we do this and make sure that our tables for y2 and y3 match, and they do. We do get an error message here and 0 here. Actually, the error message is correct. The function, both the original 1 over x and the ln of absolute value of x, both of those functions are undefined at 0, so the correct answer really is y3. Symmetric difference quotient give us a value of 0, which is actually not correct, but otherwise they do agree. Occasionally the approximation will be slightly off. One more thing, of course there's an ln button on right on your calculator. The absolute value of x on an older calculator, instead of looking like the vertical lines like we write absolute value by hand, it'll be ABS of x, and you find that in whether it's a new calculator or the old one on that TI-84 or 82 or 83, you find that as math and right arrow once to number, and it'll be the first one, math num 1. Now if we want a specific antiderivative of, let's say the specific antiderivative is g of x, where the function f of x is x to the negative 1, and we know that g of 1 is 7, well, we know that all the antiderivatives, that all the possibilities of g of x for antiderivatives look like g of x equals log of absolute value of x plus c, what we just figured out. But now, since we know an ordered pair on there, that's called an initial condition, we can solve for the missing c. In fact, this is sort of a general thing. Anytime you have an equation where it has a constant in there that's unknown, but you know it's some constant, if you can plug in an ordered pair for x and y into the formula, then you'll have an equation maybe with just that one unknown. You can solve for it. So in this case, we're plugging in 1 for x and 7 for y. That is 7 for g of x, or 7 for g. Natural absolute value of 1 is 1. Log of 1 is 0. So, of course, 0 plus c is c, so c is 7. And we get g of x as natural log of absolute value of x plus 7. We do need the absolute value, by the way, because the original function was defined both for positive and negative values, and so is the antiderivative. Now, this one, when we're going to use the fundamental theorem, remember the function that we're integrating must be not only defined but continuous on this interval. So we're integrating from 1 to 2 of x to the negative 1 dx. Notice the only places it's undefined is 0, and we have a discontinuity there. As long as our limits here do not go over 0, we can use the fundamental theorem, and that's okay here. So, of course, the fundamental theorem says if we can get our hands on an antiderivative, we just evaluate at both endpoints and subtract. And so the antiderivative is log absolute value of x. Again, I don't need to worry about the plus c when I'm doing definite integrals. Then you just evaluate that from 1 to 2. That is, plug in 2, plug in 1, and evaluate. As I said a minute ago, absolute value of 1 is 1, and log of that is 0. Log of 1 is 0. And this first part becomes the log of 2. And so the integral from 1 to 2 of x to the negative 1 dx is actually the natural logarithm of 2. Notice there's no way you're going to get a TI-84 calculator, at least, to tell you that that answer is natural log of 2, which is the exact answer. Of course, I can put in ln of 2 on the calculator, and it comes out to be about 0.69314711806 to the limits of that calculator. And if I do a numerical integral from 1 to 2 of x to the negative 1 power dx, that turns out to be exactly the same number, which is a check. If I just need the number out, if I just need a decimal approximation, I can do it two ways. I can either find the antiderivative, find the exact value, and then approximate, as I did here at the bottom, or I can just do as I did here at the top of the screen on this calculator, and that is just do a numerical integral, which is essentially Simpson's rule. Let's do a polynomial. Now, polynomial, this is going to actually use the sum rule, the constant multiple rule, the constant function rule, and the power rule. It's going to use all of those rules. So the first thing is the antiderivative of the sum is the sum of the antiderivatives. And then in each case we can bring these coefficients out front. And then we can use our power rule, our constant rule, and of course adding our c at the end, and get our answer. And of course you can actually do this completely in your head, just like you can do derivatives of polynomials in your head. We can do antiderivatives. Let's just do it in our head here. So x to the 4th, we would add 1 to the power, becomes 5 for the power, and we multiply by the reciprocal of the new power, which is 1/5. So that's the coefficient. Plus, this power goes up to 4, and multiply by the reciprocal of the new power, that's 1/4 times 2, it reduces to 1/2. Next, the power goes up to 3, and multiply by 1/3, the power is 3, and the coefficient is 1. The next one, the power goes up to 2, multiply by 1/2, that becomes 5/2 for the coefficient. Once you get a constant term, you just multiply it by x. That's our constant. Constant function rule, or linear, which is our linear differentiation rule. And then, of course, you always have the plus c. So notice what happens when you take a derivative of a polynomial. Each term goes down 1 in power, and the derivative of that constant at the end is 0. When we take an antiderivative, each power goes up 1, and then we have to add in a constant term at the end. And so when you take a derivative of a polynomial, you get a polynomial of 1 degree smaller, and when you take the integral or antiderivative of a polynomial, you get a polynomial of 1 degree larger. And of course, how will we check that? We just check that, as we always do for any of these problems, by taking the derivative of the answer and making sure it's the thing we started with, the integral. And of course, we're just using the basic derivative rules for polynomials. Should be pretty good at this by now. 5 times 1/5 is 1 times x to the power 4. 4 times 1/2 is 2, the power goes down to 3. 3 times 1 is 3, power goes down to 2. Right here. 2 times 5/2 is 5 for the coefficient, power goes down to 1. When you have an x, the derivative is just the coefficient, which is 1, and the derivative of c is 0, and so we get that. We can check it by taking our answer, 1/5 x to the 5th plus 1/2 x to the 4th, and so on. Put that in here. It's running off the screen here in the new operating system, but there it is in the y1. y2, just leave it like this. In fact, if I were doing a lot of calculus, I would just put this in as y2 and leave it. If you don't need it, you just put your cursor on the equals, hit enter. It turns it off so it doesn't show up in the table or the graph. You can turn it on when you need it. And then you can always check a derivative problem or antiderivative problem. To check an antiderivative problem, put your answer in y1, and then y3 is the original function, the original integrand, and y2 and y3 should match. Make sure you're looking at the tables for those two. And of course, it did check for us here, so we did that one correctly. Alright, here's another way we could phrase this. Suppose we are given that f prime is that original function, x to the 4th plus 2x cubed plus 3x squared plus 5x plus 1, and we know f of x, or f of 1, is 2. Find a formula for f of x. Well, we know a formula for f of x must be one of the antiderivatives. So it looks like 1/5 x to the 5th plus 1/2 x to the 4th plus x cubed plus 5/2 x squared plus x plus c for some c. Now we simply plug in the 1 and the 2, 1 for the x, 2 for the f or y, and then this allows us to solve for c. Now these 1's to any power all 1, so we end up with just the sum of the coefficients on the right, 1/5 plus 1/2 plus 1 plus 5/2 plus 1 plus c. Let's see if we can do this out here. See, 5/2 plus 1/2 is 6/2, which is 3, plus 1 is 4, plus one other one is 5. And then getting c by itself, I'll subtract these two. So our common denominator is 5. So 10/5 is 2. Multiply top and bottom of that by 2. And we're also going to do 5 is 25/5. So we have that. Now these are negative because we've subtracted from both sides. So anyway, negative 25/5 plus negative 1/5 is negative 26/5 plus 10/5 is negative 16/5, and that's your c, and so there's your function. If you take its derivative, we get this original one. If you plug in 1, you get out 2. Compute the exact value and decimal approximation of the following definite integral. The exact value is a whole number in this case, so we take that. That's the same integrand as before, and it's a polynomial, so it's continuous everywhere, so it doesn't really matter what the limits are. We know we can do this definite integral, and we can do it by the fundamental theorem. So we can take the antiderivative we came up with, again, don't have to worry about the plus c, and just go from negative 2 to 3. That is, take this formula, put 3 in place of all the x's, minus this formula with negative 2 in place of all the x's. Notice the big set of parentheses here and here. The first one, of course, we can drop, but the second one's going to distribute a minus throughout. So if we just kind of work through this, 3 to the 5th is 243 times 1 is 243 over 5. And so over 5 there. 3 to the 4th is 81 times 1/2 is 81/2. 3 to the 3rd is 27. 3 squared is 9 times 5 is 45, and that's over 2. And then we got plus 3. Now let's see, here we have 5 negatives, and a 6th negative in front makes a positive. 2 to the 5th is 32 times 1/5 is 32/5. Here we have 4 negatives and one more in the front. That makes an odd number of negatives, so the next term is going to be negative. 2 to the 4th is 16 divided by 2 is 8, so that's negative 8. The next one is 3 negatives here and one more in the front makes a positive. 2 to the 3rd is 8. Here we have 2 negatives and one more in the front makes a negative altogether. One of those 2's will cancel the denominator, and we have the other 2 times 5 is 10, but it's negative. And of course this negative 2 becomes positive 2 because of that negative. And combine like terms here, let's see what we got. 81 plus 45, 81 halves plus 45 halves, that's 126 halves, which is 81. And 243 fifths plus 32 fifths, that's 275 fifths, and that'll reduce nicely. Anyway, you just add all these up. You can use a calculator if you want. Just add those up, and it turns out nicely at exactly 140. And of course, we can check that by doing the integral from -2 to 3 of that function that we started with, dx. Since I'd already typed this in as y3, I got a little bit lazy and saved myself a bit of time. Since it was already in as y3, I just said the integral from -2 to 3 of y3 dx. And of course it was 140 as we saw. Now this one looks a little bit nastier, but it's not really. We just have one extra step, and that is to rewrite this as a sum of power functions. So 5 over x squared is 5 times x to the -2. 4 over x could be 4 times x to the -1, but I prefer to leave, if it's -1, I prefer to just leave it 1 over x. So we left that one alone. And the last one, the square root of x, is x to the 1/2 power. Now, antiderivative sum is a sum of the antiderivatives. So the antiderivative of the original function is the antiderivative of this, with the new, thinking of it in terms of power functions. And we got 3 antiderivatives. Okay, this first part, I add 1 to the power. -2 plus 1 is -1. Multiply by the reciprocal of -1, which is -1, times the 5 is -5. The next one, I can use the constant multiple rule here and bring the 4 out from front. And the antiderivative of 1 over x dx is the logarithm of absolute value of x times 4. And in the end, here I have the antiderivative of -x to the 1/2. Add 1 to the power, that becomes 1/2 plus 1 is 3 halves. 1/2 plus 2 halves is 3 halves. And we multiply by the reciprocal of the new power, which is 2/3 times the -1 that's already out there, is -2/3, and you put a plus c. Notice I don't need a plus c for every term. I can combine all those constants into one single constant at the end. Now that is the answer, but I'm going to rewrite it more like it looked to begin with. X to the -1 is 1 over x, so this first term becomes -5 over x. The next term is 4 ln absolute value of x. And then I've got x to the 3 halves is x to the 1 and 1/2. So here the 1 is the x, the 1/2 is the square root of x. So we can leave it like that. In fact, we could actually drop the absolute value on this logarithm this time, only because we already know that x has to be a positive number for this square root to be defined. So if x is positive, the absolute value of x is x, and so we can drop that if we want. Probably should. Alright, so how can we check this? Take our final answer right here, plug that in the original y1, put the original function as it was up here, put that function in y3, and you can see that I did that, and check that the derivative of y1 is y3 by checking these two, y2 and y3, against each other in the table, and we see that it does match. Now if we know that this original function here were the derivative, and we know a point on that derivative, we can find the original function, we can reconstruct the antiderivative f, a specific one. In general, antiderivatives, we just found out for functions with this derivative are -5 over x plus 4 ln of absolute value x minus 2/3 x times square root of x plus c for some constant, plug in 1 for x, 3 for y, and we can solve for what that constant is. Let's see. 1 is nice because the log of 1 is 0, so that makes that term go away. Square root of 1 is 1, and that's 1, so that kind of goes away there. So we end up with -2/3 there, 0 there, -5 there, and combine these and then subtract from both sides, and we get c is 26/3. So plug that back in place of c in the original, and now we have the specific antiderivative that we're looking for. If you do the derivative of this formula f, you're going to get this f prime right here, and if you plug in x is 1, you're going to get 3 at the end for the y. Now how about finding an a definite integral. So if we want to compute the exact and decimal approximations values of the following definite integral, that's the same integrand as before, so we get the same antiderivative, we just want to evaluate from 1 to 4. Take this formula here, plug in 4, and the same formula plug in 1. Once again, the 1, a lot of things are going to cancel out here. Working our way back, let's start at the beginning, I guess. Here we have negative 5 fourths, so we have 4 log of 4. And let's see, the square root of 4 is 2, times 4 is 8, times 2 is 16, so this is negative 16 thirds. Alright, we got to distribute this minus 2, so we got 2 minuses makes a plus 5. This term is 0, so it goes away. And 2 minuses make a plus here, and that's just 2 thirds at the end, so plus 2 thirds. Combine like terms here. The 4, ln of 4, can't combine really with the others. But the others I could get a common denominator. Common denominator of 4 and 3 would be 12. Be a least common multiple of those denominators, so it would be least common denominator. Add those 4 numbers there, and it turns out to be negative 11 twelfths. Notice that log of 4 is log of 2 squared. A property logarithm says I can bring that power out front and multiply by the coefficient. So probably the best way to write this would be 8 ln of 2 minus 11 twelfths. That's the exact value. Approximation, I can find that on the calculator by typing it in as I did here at the bottom, and we get that's about 4.6285, etc. We can also get the decimal approximation, if that's all we needed, by just doing it on the calculator by typing in the integral of 1 to 4 of the original function dx, and we get the same numerical value, and that tells us the answer if we just need a decimal answer and we don't have to do all this other stuff. On the other hand, if we want an exact answer, which is 8 ln of 2 minus 11 halves, then this gives us a way to check that. Alright, here's another example. A couple more here. So this example, we're looking at the sum of a couple of exponential functions. Well, first of all, the antiderivative of the sum is the sum of the antiderivatives. And the antiderivative of the e to the x is e to the x, and that 5 is times that, so it's 5e to the x. And the antiderivative of 3 to the x is 3 to the x, but then you divide by, or ln of 3, or multiply by 1 over ln of 3. And of course you always have plus c at the end. How do we know that's true? Well, if we took the derivative of this, we get back what we started. The derivative of the sum is the sum of the derivatives. Let's work on this way. The derivative of 5 times e to the x is 5 times the derivative of the e to the x. The derivative of the e to the x is e to the x, so the derivative of that first term is 5e to the x. The derivative of the middle term, 1 over ln of 3, is a constant, so we keep that there. And the derivative of 3 to the x is 3 to the x times ln of 3. Well, the ln of 3 cancels the 1 over ln of 3 here, leaving us just with 3 to the x, and the derivative of c is 0. Once again, we can check it without a calculator, or with a calculator, with the technology, by letting y1 be our final answer. Choose whatever c you want. I think I'll use 0. Let y2 be the numerical derivative of y1, and then y3 be the original function, just like it is, and check that y2 and y3 match, which they did. If we want an exact value for a particular antiderivative, for example, here we have f prime of x is 5 e to the x plus 3 e to the x, and we know that f of 0 is 3. We want to find a formula for the specific antiderivative f of x. We know the general antiderivative is 5 e to the x plus 1 over ln of 3 times 3 to the x plus c, so we just have to figure out what c is. Well, we do that by plugging in the x and y values that are given. F of x is 3, or y is 3, when x is 0. Plugging in x to 0, e to the 0 and 3 to the 0 are both 1. So this becomes 5 plus 1 over ln of 3 plus c equals 3. Subtract 5 from both sides. 3 minus 5 is negative 2. But we can't really combine the logarithm with that, so we see that c is negative 2 minus 1 over log of 3. And so f of x equals 5 e to the x plus 1 over the natural logarithm of 3 times 3 to the x minus 2 minus 1 over natural logarithm of 3. That's the exact formula for that specific antiderivative. If you take its derivative, you'll get the original integrand, and it goes through the indicated point. How about finding a definite integral? Same function, so we got the same antiderivative, 5 e to the x plus 1 over ln of 3 times 3 to the x. but we want to just evaluate it from 0 to 2. That should not have the plus c. Let's get rid of that. So we don't worry about the plus c. And then this is plug in the top number, plug in the bottom number. Now these to the power 0 are 1. We've got to distribute the minus. This becomes minus 5 minus 1 over log of 3. 3 squared is 9, so that's 9 over log of 3. And we have that. And we do a little combining terms here. 9 over log 3 minus 1 over log 3 is 8 over log 3. So we get 5e to the second plus 8 over natural log of 3 minus 5, which is about 39.227194131. That last number is a decimal approximation. The exact value is the next to last line, 5e squared plus 8 over ln, and then minus 5 here. So we see that this works out to be approximately 39.227, which we can get by taking the exact value and typing it in the calculator and then having it approximate for us. We can also get the approximate value by doing the numerical integration on our calculator and see that those are the same, which is our check. But the exact value is this line right here, 5e squared plus 8 over ln of 3 minus 5. Well, that brings us to the end of this video, and in the next video we'll learn how to use integration using substitution, which is essentially reversing the chain rule. That will open up a lot more possibilities for us.